Okay, so we're back. We're going to look at sections 5.3 and 5.4 in the book, which is about the double angle, power reducing, half angle, product to sum, and sum to product formulas. And this will be the last set of, I think, the last set of identities that we need to know. So what are the double angle formulas and the half angle formulas? So we have the sum formulas from last time. Cosine s plus t is cosine s times cosine t minus sine s times sine t. Sine of s plus t is sine of s times cosine t plus sine of t times cosine s. Tangent of s plus t is tangent of s plus tangent t, 1 minus tangent s tan t. We'll not be doing a whole lot with tangent. So double angle formulas are pretty easy to derive. You just set s and t to be equal to each other. So cosine of 2t is cosine of t plus t, so we just use this formula. You get cosine t minus sine t, which is cosine squared t minus sine squared t. Same thing here. If you set s and t equal to each other in this formula, you get sine of 2t is 2 sine t cosine t. If you set s and t equal to each other here, you get tangent of 2t is 2 tangent t over 1 minus tangent squared of t. So those are the double angle formulas. So cosine 2t combines with the Pythagorean identity cosine squared t plus sine squared t equals 1 to give you a couple of nice formulas. So here's the Pythagorean identity again. And the formula for cosine 2t, cosine squared t minus sine squared t equals cosine 2t. And so if we add these together, what happens? We get 2 cosine squared t. These cancel out, equals 1 plus cosine 2t. And this relates cosine squared to cosine 2t. Note a couple of different things here. One is that this has got a squared in it. This doesn't. This has got a 2t. This just has a t. And we can get another formula. We take the Pythagorean identity and the formula for cosine 2t. And now we subtract instead of adding. Cosine squared minus cosine squared is 0, so these two basically cancel out. Sine squared minus sine squared is actually sine squared plus sine squared. So 2 sine squared of t. Then we subtract, we get 1 minus cosine 2t. So what this gives me then is I've got cosine 2t in terms of 2 cosine squared. I've got cosine 2t in terms of 2 sine squared. But I also have cosine squared in terms of cosine 2t, sine squared in terms of cosine 2t. Okay, so we can get half angle formulas from this, which are kind of nice. So cosine squared of t is 1 plus cosine of 2t over 2. I just took this formula here and divided both sides by 2. So what that tells me then is that if I take square root of both sides, cosine of t is equal to plus or minus the square root of 1 plus cosine 2t over 2. And it's always easier to write the square root after you've written down the stuff inside. And there we go. So why is this a half angle formula? Well, this angle is half of this angle. So we'll set s to be equal to 2t. What that means is that t is s over 2. And if I substitute that in, I get cosine of s over 2 equals plus or minus 1 plus cosine of s over 2 square root. Okay, so what that tells me that is that if I know an angle, if I know that angle, then I can find this cosine. I can find the cosine of half the angle. We can do exactly the same thing with this formula here, right? So sine squared of t is equal to 1 minus cosine 2t over 2. And again, that's just dividing both sides of this equation by 2. So take the square root, sine of t equals plus or minus 1 plus, 1 minus, here we go, 1 minus cosine 2t all over 2 inside a square root. Make the same substitution with s, and so that tells us that we can find the sine of half the angle. Sine of s over t equals plus or minus 1 minus cosine of s over 2. So it tells us that if we know the cosine of an angle, we can find the sine and the cosine of half the angle. Which sign do you take, plus or minus? Well, it depends on which quadrant the angle s over 2 is, right? So if s over 2 is, say, in the third quadrant, right, sine would be negative, cosine is also negative in the third quadrant, for example. So these are the half angle formulas. Tangent of s over 2 is, these are the half angle formulas written nicely so that you don't have to rely on my horrible handwriting. To find tangent, that's just sine over cosine, divide those two by each other, and you get the equation for tangent of s over 2. So can we do some examples with these? So sort of two types of problems, triangles and quadrants. So here is a triangle. What we want to know is what's the exact values of cosine of 2t and cosine of t over 2. Okay, and so if we think of this as being somewhere in the xy plane, it's like that. So this is in the first quadrant. Great. So cosine 2t is what? Well, we need to know what cosine t is, sine t is, but that means we need to know what c is. So first off, Pythagoras' theorem, 12 squared plus 8 squared equals c squared. And if you actually add that all up together, you should get 208 equals c squared. So c squared is 208. And I know that can be simplified, but I'm not going to bother, and you shouldn't bother either. Great. So we know that cosine of t is 12 over square root of 208. We know that sine of t is 8, opposite over hypotenuse, right? Over 208. So cosine 2t is cosine squared t minus sine squared t. But cosine of t is this. So we replace the entire cosine with 12 over square root of 208. Now we square it because that's cosine t. And then minus sine t is 8 over square root of 208. I should remember to do the square roots after I write the thing inside them. Okay. 208. Square root should come over there. There we go. Squared. And if you grind that out, this is 144 because that's 12 squared minus 64 squared over 208. And that turns out to be 80 over 208. Those are integers, and integers you should simplify, divide down if you can. That becomes 5 over 13. So whatever 2t is, we don't know what t is, but if we doubled it, we would get a cosine of 5 over 13. Cosine of t over 2 That's where we use the half angle formula. That'll be plus or minus 1 plus the cosine of t over, plus cosine of t over, and I'm going to need a little more space here, so I'm going to move this down a tad. 1 plus cosine of t over 2 inside of square root. Well, we know that cosine t is this, so this becomes plus or minus 1 plus 12 over the square root of 208 all over 2. And just like you should always simplify integers divided by each other, whenever you've got a fraction and a fraction, you should always try and simplify that. So I'm going to make a note here. Remember that if you have a fraction a over b, that's the same thing as saying it's 1 over b, 1 over the denominator times the numerator. So if I have this thing here inside the square root over here, that I need to simplify, the numerator, the denominator is 2, so that's going to be 1/2, so the 2 on the bottom, and then times whatever's in the top, 1 plus 12 over square root of 208. Great. And so this thing here inside this square root is the same thing as this thing, right? 1 over the denominator times the numerator. And that makes it a lot easier to simplify because that becomes 1 over 2 times 1 is square root of 208 plus 12, and then that's over 208, which is inside of the square root. And so there's our cosine of 2t. Except I like to put the integer first and then the square root. And this whole thing is inside of a square root. Okay, so that's about as simplified as I'm going to get. You can, there's some things you can do with square roots, but I'm not going to bother. Plus or minus sine question mark. Well, t is in the first quadrant. T over 2 is half that angle, so that'd be like here somewhere. So t over 2 is in the first quadrant. So we take the plus sign because cosine is positive there. Okay, so a little bit about simplification there. So suppose sine of t is 7/12 and t is in the second quadrant. What's cosine of 2t and cosine of t over 2? Same sort of problem. I'm not going to go through all the details of the simplification and everything. But here's my point. Sine of t is 7/12. That tells me that this is 7. This is 12. That's my hypotenuse. And this is my angle t, because t is in the second quadrant. And then I need to know what this is. So we do Pythagoras' theorem again. We'll actually call this A. A squared plus 7 squared equals 12 squared, and you can multiply that out a little bit. Oops, where did I write this down? And we get a squared equals 95. So a is square root 95 as a length, but it's to the left, right? So it's a negative x value, so minus square root of 95. That's a. Cosine 2t, easy enough. It's cosine squared of t minus sine squared of t. Cosine squared of t, well, cosine is minus root 95 over 12, adjacent over hypotenuse, quantity squared, minus opposite over hypotenuse, 7 over 12, quantity squared. And if you grind that out, that becomes 46 over 144, which if you reduce it is 23 over 72. So note something here. This is positive. So where is 2t? Which quadrant is 2t in? So 2t, for cosine to be positive, you have to be either in quadrant 4 or in quadrant 1. So if I take t and double it, I must have ended up here somewhere. So 2t must be in quadrant 4 because we got a positive cosine. Okay. So what's cosine of t over 2? Well, like in the same thing, this is going to be, as in the problem before, this is going to be plus or minus 1 plus cosine of t over 2, all inside a square root. And that'll be plus or minus 1 plus, now the cosine of t, where's my cosine of t, is minus square root of 95 over 12. It's my 95, it's inside a square root, it's got a minus sign, there's a 12. And that's all over 2, and then that's all inside of the square root that comes from the formula. And you can simplify that a bit, same procedure that we did before. That becomes 12 minus square root of 95 over 24. Okay, right, so just clean out that fraction and fraction. So, excellent. Plus or minus depends on what quadrant is this in. Now, what we know about our quadrants here is that this is pi over 2, and this is pi. Now, if I cut these angles in half, pi over 2 becomes pi over 4. Half of pi is pi over 2. So any angle in here, in the second quadrant, if you cut that angle in half, well, this part becomes that part, and this boundary becomes that boundary. So this entire quadrant gets mapped into here. So cosine of t over 2 is in quadrant 1. So positive sign. There's a plus sign there, if I can fit that in. Okay, so when you're taking the half angle formula, you have to figure out what quadrant your angle is in, and then if you cut that in half, what quadrant is the half angle going to be in? Okay, so, nope, too far. What are power reducing formulas? So these also come from these formulas for cosine 2t, right? And remember that the third formula for cosine 2t actually has 3 formulas, is the basic one, which is cosine squared of t minus sine squared of t. Okay, so these 2 formulas allow us to replace a squared cosine squared, or sine squared, with cosines or sines. So if we solve these 2 equations for cosine squared and for sine squared, we get those 2 things. Notice if you add those together, the cosine 2t's will cancel out. So can we rewrite sine cubed t as sines and cosines with no powers? And this means, technically, actually, a power of 1. So sine cubed of t could be broken into sine of t times sine squared of t, because something cubed is something to the first times something squared. But what we know about sine squared of t is that it can be written like this. So replace the sine squared of t by 1 minus cosine 2t over 2. So simplifying a bit, distribute the sine t, that gives me sine of t minus sine of t cosine of 2t over 2. And we often will break this into two fractions. So this is a little bit about simplification again. And then we use that same trick that we did before about, not trick, but just rewriting things in terms of 1 over the denominator, so 1/2 times sine of t, 1/2, so 1 over the denominator times the numerator, sine of t, cosine of 2t. Okay, so what does that mean that we have here? That means that we've got sine of t to the first, sine of t to the first, cosine of 2t to the first. We paid a little penalty because now we have a cosine of 2t and not just a cosine of t, but that's okay. Everything is a first power. What about sine squared of t times cosine squared of t? Can you rewrite that as sines and cosines with no powers? Well, one thing that we can remember, although we touched on it very briefly, so I'm actually pretty sure you don't remember it, but one of the formulas we had above was that sine 2t equals 2 sine of t cosine t. So hopefully you've written that down, and so that'll help you remember it. So the thing that we've got, the sine squared t times cosine squared t, that's this thing, is equal to sine 2t over 2. But the whole thing squared, because we want sine squared times cosine squared. So sine times cosine, quantity squared, equals this. So the sine of 2t over 2 squared, which is 1/4 sine squared of 2t. Right? Square the top and the bottom, rewrite it as 1 over the denominator times that. But sine squared of 2t, as we had above, is, using the double angle formula, sine squared of t is 1 minus cosine of 4t over 2. So why the 4t? Well, the power reduction formula says take the angle that you have here and double it. So if our angle is 2t, doubling it gives it 4t. In the previous problem, our angle was t, and when we doubled that, we got a 2t. So how do we finish this problem off? Sine squared of t cosine squared of t is equal to 1/4, that's from here, times sine squared of 2t, which is 1 minus cosine 4t over 2. We multiply this out, 1/4 times 2 is 1/8, times 1 is just 1/8, and then 1/8 cosine of 4t. And I've rewritten this complicated looking thing in terms of just a single cosine and a constant, but I've got a 4 there inside my cosine. Okay, so here's a table of these formulas. Right, so sum and difference formulas, double angle formulas, power reducing formulas, half angle formulas. We've talked about the double angle formulas, the power reducing formulas, and the half angle formulas. Sum and difference formulas are going to come up. I swiped this from page 679 in the textbook. One thing that always comes up at this point is how much of this stuff do you have to memorize? Hopefully, if you're doing all the homework and doing all the My Math Lab by repetition, you will get a lot of this stuff. These two are super important, and so you should remember that. Almost all of these are things that you should just be able to look up, although I'll say these two are kind of important. These all come from cosine 2 theta, so that's not too bad. Tangent squared theta is this over this. That just comes from dividing sine squared theta by cosine squared theta, right? It's this term divided by that term gives you this. And the half angle formulas also come from this. Half angle formulas generally don't need to memorize them. You can look them up. Also, how do we get these extra tangent formulas? Well, clearing out the denominator, right? So if you multiply both top and bottom of this by square root of 1 minus cosine alpha, then you get rid of the square roots and you'll end up with that. But you really don't need that very often. So part of the assignments, the homework, part of making you write things out on the lecture notes is that by writing out the formulas and using them again and again, they sink into your memory without actually having to memorize them. So here are the product to sum and sum to product formulas. Again, these are probably not ones that you want to think about memorizing. What they do is they take two trig functions, the basic trig functions, sine and cosine, with different angles, s and t, multiply them together. And what you can do is represent this multiplication of sines and cosines in terms of additions or subtractions. Right? So an addition, a subtraction, an addition, an addition, a subtraction. Sum to product formulas. Here we take additions and subtractions of sines and cosines with two different angles, and we can turn them into a product. And these are useful in various places. So it's good for you to see them. Where do these come from? They come from the sum difference formulas, right? So these are all the sum difference formulas. There's 6 of them, and I'm just going to put boundaries here so it's clear. Cosine of s plus t, so two angles added together, that gives you a multiplication of two angles. Sine of s plus t, that gives you a multiplication of two angles. Tangent of s plus t, you get tangent of s plus tangent of t, it's complicated. Cosine of s minus t, again, you get angles, sines and cosines multiplied together. Same thing for s minus t, you get sines and cosines multiplied by together. So this is the derivation of this equation. So how do we get that? It's actually a lot simpler than it looks. We just take this side, right, and expand it. So 1/2 cosine of s minus t minus cosine. In fact, this is the same sort of thing that you do to verify an identity, right? Except I'm calling it a derivation now. Well, cosine of s minus t, that's this formula. So that's cosine of s, cosine of t, plus sine of s, sine of t. Cosine of s plus t, that's this formula. So it can be minus, and we'll put a parentheses around there, cosine of s, cosine of t, minus sine of s, sine of t. Parentheses, big bracket. So this becomes 1/2 of what? Well, cosine s, cosine t, cosine s, cosine t, this one's got a minus, so that term cancels this term. Sine s, sine t, minus, minus, those to get together and become a plus. So inside the brackets, I just have 2 sine s, sine t. And if I cancel out the 2's, I get that, which is what I was looking for. So right-hand side equals left-hand side. It's like proving an identity. So I might need some more space. So I'm going to move this up a tad. Okay. So what about this one? Sine s plus sine t equals 2 sine s plus t cosine s minus t. Well, there's not much I can do with that, but there's a lot I can do with this. So what I'm going to do is I'm actually going to, well, we'll just start writing. So 2 times sine of S over 2 plus T over 2 times cosine of S over 2 minus T over 2. So first thing I'm going to do is separate these, make them two angles, S over 2 plus T over 2, S over 2 minus T over 2. Okay, so sine of two functions added together is, so we have a 2 and then we have our square bracket. That's going to be sine of, oh, we're going to need parentheses here, sine of S over 2 times cosine of T over 2 plus sine of T over 2 times cosine of S over 2. And so that's my sine of S over 2 plus T over 2. Keep in mind that sine of two angles, we use S and T, we'll just call it A and B, is sine of A cosine of B minus, plus actually, sine of B cosine of A. So using this formula to expand that with A equals S over 2 and B equals T over 2, cosine of S over 2 minus, oh, sorry. The formula for addition of cosine functions is cosine of A minus B is cosine of A cosine of B, and then it should be plus sine of A sine of B. Okay, so that's where these are coming from. Sine of two angles added together mixes the sine and cosine. Cosine has the sines and cosines together. So then this will give me cosine of A minus B, cosine of S over 2 minus T over 2 would be cosine of S over 2 times sine of T over 2 plus sine of S over 2. And now I'm running out of room, which kind of sucks. And then times, what am I doing? I ran out of room and I made a mistake. So I'm going to erase all that and rewrite this. It's cosine of S over 2 cosine of T over 2 plus sine of S over 2 times sine of T over 2. And I have to close this parentheses and then close the whole bracket. Yay, so there we go. And that just looks awful, and it is in some ways. But I've got 2 times a bunch of stuff, and I'm going to put it into a big, huge bracket because it's going to be 4 terms. Because what have I've got? I've got this plus this times the quantity, this plus this. Got to FOIL things out. So first, outer, inner, last. So first is this one times this one. Note that there's a cosine of 2t in both. So we get cosine squared of 2t times sine of S over 2 times cosine of S over 2. And I'll just write cosines first because why not? So that's first. Outer is this term times this term at the end, and that's got a sine of S over T2 and another sine of S over 2. So I'm actually going to write that over here. Sine squared plus sine squared is, oh, sine S over 2 times sine S over 2 gives me a sine squared over S over 2. Then I get a cosine T over 2 times a sine T over 2. Okay, and there's a reason why I put that down there. So that's outer, inner is this one times this one, and that's got a cosine s over 2 on both. And so we're going to put that down here. So plus cosine squared of s over 2. That's this times this, and then I've got a sine t over 2, cosine t over 2. Oh, I'm running out of space again. T over 2. There we go. And you can see why I want to do that, right? Cosine squared of s over 2, sine squared s over 2, that's a Pythagorean thing. So since I've got this big gap here, we'll put the last and give it some space. Sine t over 2, cosine s over 2 times sine s over 2, sine t over 2. That means I've got a sine squared t over 2 times a cosine s over 2 times the sine of s over 2. So if I FOIL all this out, these are the 4 terms that I get. And this is actually very nice because, and now I can include more space, I have a 2 cosine s over 2 sine s over 2, cosine s over 2 sine s over 2. I can factor those out. So I have a cosine s over 2 sine s over 2, and then I'm left with cosine squared plus sine squared. Okay, plus, that's these 2 terms now. Got a sine t over 2, cosine t over 2, cosine t over 2, sine t over 2, so I can factor those out. Cosine t over 2, sine t over 2. What's left after I factor that out? Cosine squared s over 2 plus sine squared s over 2, s over 2, end parentheses, and big bracket. Oh my gosh. So this is 1. This is 1 because those are the Pythagorean identities. So we have 2 times cosine s over 2 sine of s over 2 plus cosine t over 2 sine t over 2. And if you ever see cosine times sine, remember that cosine of a, 2 cosine of a, sine of a is equal to sine of 2a. So cosine of an angle times sine of the same angle, that's sine of the double angle. So cosine s over 2, sine of s over 2 multiplied together is going to be 1/2, right? If I divide both sides by 2, 1/2 of twice the angle. So this is going to be sine of twice s over 2, which is just s, all divided by 2. And then this will be sine of t over 2, right? Because if this is a, is s over 2, you need double it. When you double s over 2, you get s. Distribute the 2 and you get sine s plus cosine s, which is messy as heck, but on the other hand, it's also very straightforward. Just substitute in the formulas, multiply everything out, and then apply the sine 2a formulas. So what this allows us to do is that we can turn products into a sum. And sometimes a sum is easier to deal with than a product. So what we know is that if we have cosine of s times sine of t multiplied together, then we have a formula for that, which is 1/2 of sine s plus t. So this is just copying down the formula from above, minus sine of s minus t. Great. So s is 3x over 2. It's the angle that's inside the cosine. T is 5x over 2. It's the angle that's inside the sine. So s plus t is 8x over 2, which is 4x. S minus t is 3x over 2 minus 5x over 2, which is minus 2x over 2, so it's just minus x. So cosine of 3x over 2 times sine of 5x over 2 is equal to 1/2 sine of s plus t, but that's just 4x, sine of 4x, minus sine of minus x, because that's my s minus t. But remember that sine is odd. Sine of minus x equals sine of x. So we can simplify this a little bit. 1 equals, sorry, minus sine of x. So sine is odd means sine of minus x equals minus sine of x. So 1/2 sine of 4x. Odd functions basically means you can take the minus sign that's inside the function and take it out. This minus sign times that minus sign will just give me a plus. And then just rewriting it after I distribute the 1/2. Plus 1/2 sine x. So sometimes dealing with addition is easier than dealing with multiplication. Sometimes dealing with multiplication is easier than dealing with addition. So what's the exact value of sine of 75 degrees and sine of 15 degrees using a sum to product formula? So we've got sine of 75, sine of 15. So sine of s plus sine of t, we have a formula for that. And that's 2 sine of the sum over 2 times cosine of the difference of the angles over 2. Okay, so here we're having s equals 75 degrees, t equals 15 degrees, s plus t equals 90 degrees, and half of that is 45 degrees. S minus t is 75 minus 15 is 60 degrees, and half of that equals 30 degrees. Okay, so this becomes 2 sine of 45 degrees times cosine of 30 degrees. And those are part of our 45, 45, 90, 30, 60, 90 triangles. Sine of 45 degrees is 1 over root 2. Cosine of 30 degrees, that's going to be the long side. Right? 30, 60, 90 is like that. That's 1/2. This is root 3 over 2. There's 30 degrees. So this will be square root of 3 over 2. These two cancels. There should be an equal sign here. And we get square root of 3 over square root of 2. So that's the exact value of those added together. Great. So what about verifying identities with these things? So verifying identities with these new identities that we just created work pretty much the same way identifying identities did before. You just have to recognize the new formulas. So here I'm going to add an extra question, which is, how do you tell if something is an identity, right? Which one of these two actually is an identity? And it's not that bad, right? We can look at this one and say, well, this is a function, call it f of t, and this is a function. Two functions are equal means that their graphs are the same. So if we graph both of these things, and so I'm going to share a different screen real quick, if I can find it. There it is. So here's GeoGebra. We'll zoom in a little bit. This is the graph of cosine 4 to the x, sine 4 to the x. That's that function. The other function that we had was g of x equal to, is this equal to cosine of 4x? Great. So the green function is cosine 4x plus sine 4x. The red function is cosine 4x. These are different functions, right? They have different graphs. In fact, they only meet at whatever this point is, right? So they meet at those points. So these two functions are not equal to each other because they have different graphs. So if we go back to the lecture notes, cosine 4t plus sine 4t does not equal cosine of 4t, not an identity. What about this one? Well, this is a function. This is another function. If I compare the graphs, are they the same graph or are they different graphs? So let's go back to GeoGebra. Boink. Here we are. Actually, we want to look at this one. So this is 2 times sine x times cosine x times secant of 2x. That was one side of that equation. The other side that we wanted to look at was, is this equal to tangent of 2t? Oops, and we should type better. Tangent of 2t. So remember, the green line is f of x, and the blue line is g of x. And when I graphed the blue line, it went right on top of the green line. These are the same graph. There's the green line, there's the blue line, right? Except now this one's gone white. So those are the same graph, right? The graphs just lie on the top of each other, which means the functions are the same. So that's an identity, right? So if we come back to this one is an identity. And that's how you can tell if an equation actually is an identity, right? Are the graphs the same? So we can actually verify that? Well, sure. The right-hand side is equal to 2 sine t cosine t secant of 2t. Secant of 2t we know is 1 over cosine, so this becomes 2 sine of t cosine t over cosine of 2t. Note we can't have any cancellation between these two because they have different angles. This angle is twice that angle, so there's no cancellation there. But this part here, as we've noticed before, that's just sine of 2t. Now we've got the same angle, so this is just tangent of 2t because sine over cosine equals tangent. Great. But that equals the left-hand side. That's my tangent 2t. So that's the identities. Okay, so you can check if an equation is identity by just graph them. So what's the difference between a formula and identity and an equation? So anything where we've got an equal sign, right? If you've got an equal sign, then that's an equation. So, I mean, that's what it means to be an equation, is we've got an equal sign in there somewhere. So, but if we have f of t equals g of t, we can actually think of it in 3 different ways. One, it could be stating that 2 functions are equal, right? And so x squared minus 1 is equal to x plus 1 times x minus 1. You can multiply that out. If you graph this, y equals x squared minus 1, and you graph that, you get exactly the same graph. Another way to say that is if you pick any x value and you plugged it in here, here, and here, you get exactly the same thing on both sides. For whatever x, that works. So if we think of the 2 sides, x squared minus 1 and the x plus 1 times x minus 1 as functions, it's saying they have the same graph. If we think of them as being just 2 expressions, x squared minus 1 equals x plus 1 x minus 1, if I'm doing some kind of algebra, what that means is that I can replace this whenever it occurs by that. because they're equal to each other, right? And then that helps in doing algebra. Or you can replace this by that, right? So these are interchangeable things. You can switch one out for the other. A very different thing, though, is asking for a value for x, right? If I want to solve this, right, and it's important that the word solving is there. If I want to solve this, that means find the particular x values that make the equation true. In general, this is a parabola, this is a parabola, this is a line, right? They're not equal to each other. They intersect only when x equals 1. That's the only number you can plug in so that you get the same thing on both sides. If you plug in x equals 1, the left side is 0, the right side is 0. If you plug in x equals 2, then the right side will be 3 and the left side will be 2, which will be false. So all three of these are called equations because they have equal signs, but there's a difference between the third case and the first two. In the third case, some x values make the equation true, but some make it false, and the goal is to find the x values that make it true. Identities and formulas, every x value works as long as the x value is in the domain. And the two sides of an identity or formula, just different ways to write the same thing. Okay, and last, a little bit of historical stuff. What do trig identities have to do with the scientific revolution? So to do astronomy, you need to know your sines and cosines because planets go around in circles, well, ellipses, and they repeat their behavior, which means you need trig functions to describe them. In 1543, Nicholas Copernicus published On the Revolutions of the Heavenly Spheres, which is one of these books that is viewed as kicking off the scientific revolution. And the first thing he does in this book, if you actually go and read it, is that he builds a table of sines. And the key thing here is you need to know what sine of 1 degree is, because you can find all the other signs using addition formulas. But how do you find that? Well, you know what sine of 30 degrees is, that's 1/2. And so using the half angle formulas, half of 30 degrees is 15, half of that is 7.5, half of that is 3.75, half of that is 1.875, and finally half of that is whatever this number is, 0.9375 degrees. Oh, I might have rounded this. So by using the half angle formulas, you can find an angle that's very close to 1, and you can figure out what the sine of that is because you have the half angle formulas. And at each step, you're going to need to actually calculate the cosine of all those things as well. Sine of 45 degrees is 1/√2. We know that. Applying the half angle formula is 9 times. You can find sine of this very small number as well as sine of, as well as the cosine of that number. But this number that we got by having 30 degrees and this number that we got by having 45 degrees is really, really close to 1. So you can get the addition formulas to get you sine of this, and that's very nearly sine of 1, and then you can use something called linear interpolation to get the value of sine of 1 degrees. Once he had that, he can build his sine table. Here are the sines of all the things, and then he can make his argument that the Earth went around the sun and not the sun around the Earth. Keep in mind that as he's doing this, he has no calculator, so he had to do all of this by hand. And now we have computers and stuff, and so we can just graph things quickly and make the computer calculate stuff. So that's that. And I should stop